The ice was forming wrong, and Geoffrey Pyke had maybe 6 weeks before the demonstration that would either convince Churchill that aircraft carriers could be built from frozen wood pulp, or would prove the entire concept was scientific fantasy that had wasted months of wartime research. He stood in the refrigerated testing facility watching technicians struggle with ice blocks that kept cracking under stress tests, calculating whether adding sawdust to water before freezing would create material strong enough to support aircraft operations at sea, or whether Pykrete, his invented icewood composite, would simply be elaborate failure that looked brilliant on paper but couldn't survive contact with engineering reality. The Atlantic was killing merchant ships faster than replacements could be built, and U-boats were operating with impunity in mid-ocean gaps where Allied aircraft couldn't reach them, and Pyke's solution was constructing unsinkable aircraft carrier from ice that would patrol those gaps and close the air coverage hole that was costing thousands of lives monthly. The concept had emerged from Pyke's recognition that ice was abundant free material that could be manufactured anywhere with freezing temperatures and water, that ice ships would be immune to torpedo damage because ice didn't sink, and holes could be patched by simply spraying more water that would freeze. The limitations of pure ice were obvious. Ice was brittle and would shatter under stress. Ice melted in warm water, which meant ships would dissolve before completing Atlantic crossing. Ice couldn't support structural loads that aircraft carrier required. But Pyke had theorized that mixing wood pulp or sawdust into water before freezing would create composite material that combined ice's abundance with wood fiber's structural strength, would create Pykrete that might actually work as construction material for ships that conventional materials couldn't economically produce. The testing program that Pyke was supervising had revealed that Pykrete was dramatically stronger than pure ice, was tough enough to resist fracture under impacts that would shatter regular ice, was insulating enough that melting was substantially slower than pure ice would experience. The improvements were encouraging, but they weren't sufficient. Pykrete was still weaker than steel or concrete, still melted eventually in warm water, still required refrigeration systems to maintain structural integrity during operations. The material properties suggested Pykrete ships were theoretically possible, but the engineering challenges of actually building and operating them remained formidable enough that many engineers doubted the concept would ever be practical, regardless of how impressive laboratory tests appeared. Churchill's interest in the project had been captured by demonstration, where Pyke had shot bullets into ice block and into Pykrete block, showing that bullets shattered pure ice, while Pykrete absorbed bullets with minimal damage. The demonstration had been theatrical and had impressed Churchill enough that he authorized continued research despite skepticism from naval architects who considered ice ships as absurd, regardless of how strong Pykrete was compared to regular ice. Churchill saw potential strategic advantage in ships that could be built quickly using abundant materials, saw possibility of solving U-boat problem through unconventional approach that German planning hadn't anticipated. The support from highest political levels gave Pyke resources to continue development, but also created pressure to demonstrate practical viability within timeline that political patience would permit. The demonstration Pyke was preparing would be at Quebec Conference, where Churchill would meet with Roosevelt and where Allied strategic planning would determine resource allocation for various competing war efforts. Pyke needed to demonstrate not just that Pykrete was strong material, but that ships built from it would be operationally viable, would survive Atlantic conditions, would provide aircraft platforms that could actually conduct anti-submarine operations. The demonstration required showing Churchill and skeptical military officers that ice ships were credible rather than fantasy, required providing evidence that would overcome instinctive reaction that ships built from ice were obviously impossible, regardless of what laboratory tests suggested. The engineering challenges were extraordinary and numerous. Pykrete ships would need refrigeration systems powerful enough to keep hull frozen despite warm seawater and despite tropical sun. The refrigeration would require enormous power, which meant massive engines, which meant the ship would be heavy, which meant it needed to be huge to provide adequate buoyancy. The calculations suggested ice aircraft carrier would need to be approximately 2 million tons displacement, roughly 10 times larger than conventional carriers, and would need to be maybe 3,000 feet long to accommodate flight deck operations. The scale was unprecedented, and the construction would require resources and time that might exceed what conventional steel carriers would require, despite Pykrete's supposed advantages. The structural engineering was complicated by Pykrete's unusual material properties. Unlike steel or concrete, Pykrete was viscoelastic material that deformed slowly under sustained loads, that crept and sagged in ways that conventional ship design didn't account for. The behavior meant ship structure would need constant monitoring and adjustment, would need refrigeration precisely controlled to maintain material properties within acceptable range, would need engineering approaches that no shipbuilder had experience with because no one had ever built large structures from frozen materials that required artificial cooling to prevent dissolution. Pyke had named the proposed ship Project Habakkuk, after biblical prophet, though whether the spelling with extra B was intentional reference or error that became fixed through repetition remained unclear. The name was evocative and memorable, which helped with political presentation, but didn't address fundamental engineering questions about whether Habakkuk was feasible or was merely interesting theoretical exercise that would never become operational reality. The name became associated with ambitious project that pushed technological boundaries, but also became shorthand for proposals that seemed brilliant conceptually, but which collapsed under practical scrutiny. The prototype construction was happening at Patricia Lake in Canadian Rockies, where winter temperatures would naturally maintain freezing conditions that Pykrete required. The prototype was smaller-scale model, maybe 60 feet long, that would demonstrate construction techniques and would provide test platform for studying Pykrete behavior under conditions approximating shipboard use. The construction was proceeding slowly because working with Pykrete required techniques that construction crews had to develop through experimentation, required learning how frozen wood pulp composite behaved differently than familiar materials that conventional construction methods were designed for. The refrigeration system testing was revealing that keeping Pykrete frozen would require industrial-scale cooling equipment that would be extraordinarily expensive and heavy and complex. The cooling requirements were manageable for stationary structures in Arctic conditions, but became progressively more challenging for mobile ship operating in warm Atlantic water and exposed to solar heating. The calculations suggested Habakkuk would need refrigeration capacity equivalent to several large industrial plants, would need that capacity operating continuously throughout deployment, would need fuel supplies to power refrigeration that would consume significant fraction of ships' total carrying capacity. Churchill's enthusiasm for Habakkuk was sustained by strategic logic that conventional resources were insufficient for Atlantic battle, and that unconventional solutions deserved serious consideration even if they seemed initially absurd. The logic was sound. U-boat campaign was succeeding partially because Allied air coverage had gaps in mid-Atlantic, where land-based aircraft couldn't reach, and where conventional carriers couldn't be deployed in sufficient numbers. Ice carriers that could be built quickly might close those gaps before German submarine production could be increased to compensate, might provide temporary advantage during critical phase of Atlantic campaign when shipping losses were threatening to prevent invasion buildup. But strategic logic didn't guarantee engineering feasibility, and Pyke was increasingly concerned that Habakkuk was theoretically sound but practically impossible given wartime constraints and available technology. The ship would be a massive engineering project requiring years to complete and requiring specialized construction facilities that didn't exist and would need to be built before ship construction could begin. The timeline was incompatible with urgent strategic needs that had motivated the project initially. By the time Habakkuk could be completed, Atlantic battle might be won or lost through other means, and ice carriers would be obsolete before becoming operational. The Quebec demonstration that would determine project's future was approaching, and Pyke had to decide what to show Churchill that would be honest about engineering challenges while maintaining political support that kept research program alive. Complete honesty about difficulties would probably kill the project, but excessive optimism would create expectations that couldn't be met and would damage credibility when reality became apparent. Pyke chose middle approach, where he would demonstrate Pykrete's impressive material properties, while acknowledging that scaling from laboratory to ship introduced problems that research was actively addressing but hadn't definitively solved. The demonstration involved bringing ice block and Pykrete block to Quebec Conference and conducting live ballistics test showing material performance difference. Pyke arranged for pistol and for safe shooting arrangement that would allow Churchill and other conference participants to observe bullet impacts on both materials. The demonstration was theatrical, but it was also scientifically valid. The material property difference was real, and the ballistics test demonstrated real advantage that Pykrete offered compared to pure ice. Whether that advantage translated into viable ships remained uncertain, but the demonstration would show that foundational material science was sound even if engineering applications remained challenging. Churchill's reaction to the demonstration was enthusiastic, but tempered by recognition that impressive material properties didn't automatically mean practical ships. Churchill authorized continued research, but also asked pointed questions about construction timeline and resource requirements and operational capabilities that Habakkuk would actually provide if built. The questions revealed Churchill understood distinction between interesting technology and useful military capability, understood that continuing research required believing ultimate payoff would justify investment even if that payoff remained uncertain and distant. The naval architects who reviewed Habakkuk design after Quebec Conference were deeply skeptical about practical viability, despite acknowledging Pykrete's interesting material properties. Their analysis highlighted numerous engineering problems that Pyke's research hadn't adequately addressed. The refrigeration requirements, the structural behavior under sustained loads, the construction techniques needed for building with material that had never been used for ship construction, the operational challenges of maintaining frozen hull while conducting flight operations that generated heat. The analysis concluded Habakkuk might theoretically work, but would require solving so many unprecedented engineering problems that conventional carriers would be simpler and faster to build, even accounting for steel shortages that had motivated ice ship concept. The strategic situation that had created urgency for Habakkuk began changing during 1943 as Allied success in Atlantic battle reduced U-boat effectiveness through improved convoy tactics and through long-range aircraft that were beginning to close the mid-Atlantic gap. The improved situation reduced pressure for desperate measures like ice carriers, reduced willingness to invest enormous resources in experimental ship design when conventional approaches were showing promising results. Habakkuk gradually transitioned from urgent priority to interesting research program that might produce useful technology eventually, but which wasn't critical for immediate operational needs. The prototype at Patricia Lake never evolved beyond small-scale demonstration that proved construction was possible, but which didn't resolve fundamental questions about whether full-size ship would be practical. The prototype served valuable purpose, proving Pykrete could be manufactured at scale and could maintain structural integrity under realistic conditions. But prototype success didn't translate into decision to proceed with operational ship construction because engineering analysis consistently showed that difficulties outweighed advantages for any realistic deployment timeline. Project Habakkuk was officially canceled in 1944 when resources were redirected toward invasion preparations that had higher priority than experimental ship construction. The cancellation wasn't dramatic announcement, but gradual reduction in funding and personnel until research effectively stopped without formal declaration that concept had been abandoned. Pike continued advocating for ice ships through war's conclusion, but never regained political support that Churchill's initial enthusiasm had provided, never overcame engineering skepticism that had accumulated as detailed design work revealed practical difficulties. The legacy of Habakkuk was mixed. Project demonstrated that unconventional approaches to strategic problems deserved serious consideration and that material science could produce surprising capabilities, but also demonstrated that impressive laboratory results didn't guarantee practical applications and that engineering feasibility required more than just solving individual technical problems. Pykrete remained interesting material with legitimate advantages over pure ice, but never found application beyond small-scale uses, where its properties were valuable and where its limitations were manageable. Pike's broader career as scientific advisor and unconventional thinker was defined partially by Habakkuk, which became his most famous project despite being ultimately unsuccessful. His approach to problem-solving emphasized challenging assumptions and considering solutions that conventional thinking dismissed prematurely, emphasized that breakthrough innovations often came from reconsidering what seemed obviously impossible. Habakkuk exemplified that approach and demonstrated both its value and its limitations. The ice ship concept was creative and addressed real strategic need, but creativity alone couldn't overcome engineering realities that made implementation impractical within wartime constraints. The Patricia Lake prototype eventually melted after refrigeration was shut down following project cancellation. The melting took surprisingly long, nearly 3 years, demonstrating Pykrete's insulating properties and showing that concerns about rapid melting in warm water had been overstated. The slow melting validated some aspects of Pike's original concept, but came too late to influence project decisions that had already been made based on other considerations. The prototype's physical disappearance left minimal trace of Habakkuk beyond documentation and photographs and memories of participants who had worked on what remained one of most unusual military projects of the war. Modern engineering analysis of Habakkuk design using contemporary materials, science, and computational methods confirms that the ship would have been extraordinarily difficult to build and operate, but wasn't technically impossible, as some skeptics claimed. The analysis shows that refrigeration requirements would have been manageable with sufficient engineering effort, that structural issues with Pykrete creep could have been addressed through proper design, that construction was feasible if extraordinary resources were committed. But analysis also confirms that effort required would have exceeded what conventional carrier construction demanded, that operational limitations would have reduced military effectiveness compared to steel ships, that practical barriers to implementation were sufficient to justify cancellation even though fundamental concept wasn't proven impossible. The Pykrete blocks that were created for demonstration purposes and for various tests were preserved in frozen storage for years after project ended because no one knew how to properly dispose of large quantities of frozen sawdust composite. Eventually, the blocks were allowed to melt, and the resulting sawdust slurry was composted or dispersed without ceremony marking end of material that had briefly seemed likely to revolutionize naval architecture. The mundane disposal contrasted sharply with dramatic origins, when Pykrete had appeared to offer solution to critical strategic problem, and when Churchill had been enthusiastic about unconventional approach to Atlantic battle. Pike died in 1948, without seeing any practical application of Pykrete technology beyond small-scale uses that didn't require the massive scale that Habakkuk had demanded. His obituary mentioned Habakkuk as interesting failure rather than as achievement, mentioned it as example of creative thinking that hadn't quite worked, rather than as contribution to war effort. The characterization was fair, but incomplete. Habakkuk had demonstrated willingness to challenge conventional wisdom and had shown that material science could produce surprising results, even when those results didn't translate into operational systems. Churchill's memoirs discussed Habakkuk briefly, as interesting might have been, and as example of how wartime pressures drove consideration of unconventional approaches that peacetime planning would have dismissed immediately. Churchill never expressed regret about supporting the project, despite its ultimate failure, because he understood that innovation required accepting risks that some promising ideas would fail after consuming resources. The willingness to support unconventional projects was part of Churchill's leadership approach, and Habakkuk exemplified both the value and the cost of that approach. The scientific team that worked on Habakkuk included engineers and materials, scientists who had to develop entirely new analytical frameworks for understanding how frozen composite materials would behave under conditions that no previous research had examined. The team conducted hundreds of experiments testing Pykrete under varying temperatures and stress conditions and loading patterns, building database of material properties that would have been valuable for future applications if any had ever materialized. The research produced genuine advances in understanding ice mechanics and composite material behavior, even though the specific application to aircraft carriers proved impractical. The construction challenges that killed Habakkuk operationally were partially about scale and partially about novelty. Building small structures from Pykrete was relatively straightforward. Mix sawdust with water, freeze it, shape it as needed. But building structure measuring thousands of feet long and hundreds of feet tall required construction techniques that didn't exist and would need to be invented. The freezing process would need to be controlled carefully to prevent cracks from forming as ice expanded. The construction would need to proceed in precisely refrigerated environment that would require building massive temporary structures before ship construction could even begin. The timeline would stretch to years rather than months that Pike's initial optimism had suggested. The insulation requirements for keeping Pykrete frozen were studied extensively and revealed that protecting ice hull from melting would require thick insulating layers that would add substantial weight and complexity to ship design. The insulation would need to prevent heat transfer from warm seawater and from tropical sun, and from internal heat sources, including machinery and aircraft operations. The calculations showed insulation thickness of several feet would be necessary, which meant the ship's actual structural hull would be buried beneath insulating layers that would need their own structural support, creating nested engineering problems that compounded construction complexity. The aircraft operations that Habakkuk was supposed to support created additional challenges because flight deck needed to remain ice-free while rest of ship remained frozen. The thermal management required for maintaining different temperature zones within same structure introduced engineering difficulties that conventional carriers didn't face. Heating systems would be needed for flight deck, cooling systems would be needed for hull, and preventing heat from deck operations from warming hull required sophisticated thermal barriers that would be difficult to design and construct and maintain during operations. The personnel requirements for operating Habakkuk would have been extraordinary because crew would need to constantly monitor refrigeration systems and would need to make emergency repairs to cooling equipment that any failure could cause progressive warming that would compromise structural integrity. The crew size estimates ranged into thousands of personnel, which was substantially larger than conventional carriers required, which meant feeding and housing massive crew in ice ship that had limited internal volume available after accounting for refrigeration equipment and insulation and aircraft facilities. The personnel logistics became increasingly daunting as detailed planning revealed how many people would be needed to keep ice ship operational. The weapons and defensive systems that aircraft carrier required would need to be integrated into Pykrete structure in ways that wouldn't compromise hull integrity or create thermal problems. Gun emplacements and radar installations and other military equipment all generated heat and all required mounting points that would need to penetrate insulating layers without creating thermal bridges that would cause localized melting. The integration challenges multiplied as designers attempted to accommodate all required military capabilities within constraints that frozen hull imposed. The harbor facilities that would be needed for maintaining and repairing Habakkuk didn't exist and would be extraordinarily expensive to construct. The ship would require specialized dry dock facilities that could maintain freezing temperatures, would need refrigeration infrastructure on shore to support shipboard systems, would need trained personnel who understood how to work with Pykrete and how to repair damage without compromising structural integrity. The shore infrastructure requirements alone were substantial enough to question whether Habakkuk made economic sense, even if ship itself proved technically feasible. The strategic value calculation that had initially motivated Habakkuk was based on assumption that ice ships could be built much faster and cheaper than conventional carriers using materials that weren't constrained by wartime shortages. But as engineering details accumulated, the cost and timeline advantages largely disappeared. Pykrete was cheap material, but the refrigeration equipment was expensive. The construction techniques were time-consuming because they were novel. The specialized facilities required for construction had to be built before shipbuilding could start. The economic case for Habakkuk eroded as realistic cost estimates replaced initial optimistic projections. The operational effectiveness of ice carrier compared to conventional carrier became increasingly questionable as analysis revealed limitations that Pykrete hull imposed on ship performance. The massive size required for adequate buoyancy meant the ship would be slow and unmaneuverable compared to conventional carriers, would be vulnerable to submarine attack despite being unsinkable because torpedoes could damage flight deck and could disable refrigeration systems. The size also meant the ship couldn't enter most ports and couldn't transit Panama Canal, which would restrict deployment flexibility in ways that limited strategic utility. Pike's response to accumulating engineering skepticism was to emphasize that Habakkuk represented fundamentally different approach to naval architecture, and that criticism based on conventional assumptions missed the point of unconventional design. His argument had merit. Ice ships would operate differently than steel ships, and required being evaluated on their own terms, rather than being judged against standards developed for conventional vessels. But the argument also revealed gap between Pike's conceptual thinking and practical engineering that needed to be resolved before concept could become operational reality. The gap proved too wide to bridge within wartime constraints, even though Pike continued believing the concept was sound and that engineering problems were solvable given sufficient resources and time. The American naval officers who reviewed Habakkuk design as part of Allied planning coordination were almost uniformly skeptical and recommended against proceeding with construction. Their skepticism was based on detailed engineering analysis rather than reflexive rejection of unconventional approach, was based on calculations showing that conventional carriers could be built faster and operated more effectively than ice ships, even accounting for steel shortages that were motivating alternative approaches. The American recommendation carried significant weight because U.S. industrial capacity would need to be involved in any realistic Habakkuk construction program, and American reluctance to commit resources effectively killed any possibility of proceeding with operational ship. The political dynamics around Habakkuk involved competing visions of how to address Atlantic shipping crisis and competing assessments of what unconventional solutions were worth pursuing. Churchill's support provided political protection that allowed research to continue but couldn't overcome accumulating technical evidence that concept was impractical. The political support gradually eroded as other approaches to Atlantic battle showed progress, and as engineering difficulties made clear that Habakkuk wouldn't provide quick solution to urgent strategic problem. The erosion was gradual rather than dramatic, with project dying slowly through budget reductions and personnel reassignments rather than through definitive cancellation decision. The morale among researchers working on Habakkuk varied throughout project, with initial enthusiasm about revolutionary concept gradually giving way to frustration about practical difficulties, and eventually to recognition that project probably wouldn't result in operational ships, regardless of how much additional work was done. Some researchers left voluntarily to work on projects with clearer paths to implementation, while others remained committed to solving problems that continued research was revealing. The morale trajectory reflected broader pattern in research programs, where initial optimism collides with reality and where some problems prove more difficult than initial assessment suggested. The documentation produced by Habakkuk Project filled numerous filing cabinets with technical reports and test results and design drawings that represented thousands of hours of engineering work. The documentation was preserved in archives where it remained largely unexamined for decades because Pykrete technology wasn't pursued further and because the specific applications that project had studied weren't relevant to post-war needs. The documentation eventually became historical resource rather than technical reference, became record of ambitious project that had failed despite considerable investment and despite genuine innovation in materials science. The lessons that military planners drew from Habakkuk experience were mixed and sometimes contradictory. Some concluded that unconventional approaches deserved serious consideration because conventional solutions might be insufficient for unprecedented problems. Others concluded that unconventional approaches should be viewed skeptically because impressive laboratory results often concealed practical difficulties that only detailed engineering would reveal. Both conclusions had validity, and both influenced how subsequent proposals for unconventional military technology were evaluated in planning processes that tried to balance innovation against practical constraints. The scientific reputation of researchers who worked on Habakkuk wasn't significantly damaged by project's failure because wartime research community understood that many projects would fail and that failure didn't necessarily reflect poorly on scientists who had worked on them. The research had been conducted competently and had produced genuine insights into material properties, even though ultimate application hadn't proven feasible. The professional tolerance for failure in research context allowed Habakkuk veterans to continue productive careers without being stigmatized by association with canceled project. Pike's personal reputation was affected more significantly by Habakkuk's failure because he had been principal advocate and because his unconventional thinking style made him controversial even when his ideas succeeded. The failure reinforced perceptions among skeptics that Pike was brilliant but impractical, that his ideas were interesting conceptually but couldn't survive contact with engineering reality. The perception wasn't entirely fair. Habakkuk had failed for legitimate engineering reasons rather than because fundamental concept was absurd. But perceptions mattered more than fairness in determining Pike's influence on subsequent decisions. The post-war period saw occasional proposals to revive Pykrete technology for various applications, including Arctic construction and offshore platforms, but none proceeded beyond preliminary studies that concluded modern materials offered better performance than frozen sawdust composite, despite Pykrete's historical interest. The material remained curiosity rather than practical construction material, remained example of creative problem-solving that hadn't quite worked rather than foundation for continuing technological development. The Patricia Lake site, where Habakkuk prototype was built, eventually became tourist attraction, with interpretive displays explaining the ice ship project and its role in wartime innovation. The site preservation reflected public interest in unusual military projects and reflected recognition that failed projects could be historically significant even when they didn't produce operational results. The tourist attraction emphasized ingenuity and unconventional thinking rather than dwelling on projects' cancellation, presented Habakkuk as interesting example of how wartime pressures drove creative responses to strategic problems. Modern materials science students occasionally study Pykrete as example of composite material design and as case study in how material properties depend on microstructure and component proportions. The studies use Habakkuk as historical context, but focus on underlying science rather than on specific military application that had motivated original research. The educational use keeps Pykrete from being completely forgotten and provides context for understanding how frozen composites behave under various conditions, even though practical applications remain limited. The few Pykrete samples that were preserved in frozen storage eventually degraded as freezers were decommissioned or as storage priorities changed, and as no one remained who considered samples worth maintaining indefinitely. The material degradation meant physical evidence of Habakkuk largely disappeared beyond photographs and beyond Patricia Lake site, where outline of prototype can still be detected through underwater surveys that reveal remnants of structure that melted 7 decades ago. Churchill's willingness to support Habakkuk, despite skepticism from naval professionals, reflected his understanding that conventional approaches might be insufficient for unprecedented challenges that World War II presented. The support wasn't blind faith in untested technology, but calculated decision that potential payoff justified investment, even though probability of success was uncertain. The decision-making approach accepted that some supported projects would fail, but believed that occasional successes would justify the costs of failures. Habakkuk failed, but other unconventional projects that Churchill supported succeeded, and the aggregate results validated his approach, even though individual projects didn't all deliver hoped-for results. The engineering profession's response to Habakkuk was to develop more systematic approaches to evaluating unconventional proposals before committing substantial resources to development. The response included better preliminary analysis methods and more rigorous feasibility studies that would identify fundamental problems earlier in development cycle before extensive resources were committed. Habakkuk had consumed significant resources before engineering difficulties became apparent, and military planning wanted better filtering mechanisms that would prevent similar resource investments in projects that detailed analysis would reveal as impractical. The strategic intelligence value of Habakkuk was minimal because project remained classified, and Germans never learned that Allies had seriously considered ice aircraft carriers for Atlantic operations. The secrecy meant Germans didn't need to develop countermeasures or adjust their planning to account for possibility of ice ships, meant the project consumed Allied resources without imposing any corresponding costs on German planning. The intelligence dimension distinguished Habakkuk from projects like dummy tanks and false radio traffic that were intended to deceive enemy and that achieved value through misinformation even when physical implementation was minimal. The cultural legacy of Habakkuk extended beyond military history into popular understanding of wartime innovation and into folklore about unusual projects that characterized World War II research efforts. The ice ship became a memorable story that was retold in various contexts as example of creative thinking and as example of how desperate circumstances drove consideration of approaches that peacetime logic would reject immediately. The cultural resonance kept Habakkuk from being completely forgotten, even as technical details faded from active memory, and even as practical relevance diminished with development of modern materials and construction methods. The Quebec Conference demonstration, where Pike showed Pykrete's ballistic resistance, became legendary, partly because it involved Churchill and Roosevelt, and partly because dramatic visual demonstration made abstract material properties concrete and memorable. Stories about the demonstration often emphasized theatrical aspects, shooting bullets into ice blocks during high-level diplomatic meeting, while minimizing that demonstration proved material properties rather than proving ships were practical. The emphasis on drama over substance was typical of how technical projects become remembered through simplified narratives that capture public imagination while losing engineering nuance that determined whether ideas actually worked. The institutional memory of Habakkuk within British Admiralty became cautionary tale about how promising concepts could consume resources without delivering results, and about how political enthusiasm could drive technical programs beyond what engineering realities supported. The cautionary interpretation wasn't universal. Some planners continued believing Habakkuk had been prematurely cancelled, and that continued development would have solved engineering problems that caused project termination. The disagreement about what lessons should be drawn from Habakkuk persisted through post-war period and influenced how subsequent unconventional proposals were evaluated by officials who remembered Ice Ship Project with varying interpretations. The contribution that Habakkuk made to Allied victory was indirect and difficult to quantify. The project didn't produce operational ships, but it represented willingness to consider unconventional solutions, and it demonstrated that scientific creativity could be applied to strategic problems even when applications didn't ultimately prove practical. The contribution was atmospheric rather than material, showing that leadership was willing to support innovative thinking even when innovation meant accepting risks of failure. The atmospheric contribution mattered for maintaining research culture that produced other innovations that did prove operationally successful, even though Habakkuk itself didn't reach operational status. The final assessment of Habakkuk as historical project remains contested among historians who disagree about whether the research was worthwhile investment or whether resources would have been better directed toward conventional approaches that had proven track records. The disagreement reflects broader debates about innovation policy and about how to balance supporting creative thinking against maintaining focus on solutions that are likely to work. Habakkuk exemplifies the dilemma. Supporting unconventional ideas produces occasional breakthroughs, but also produces failures that consume resources, while avoiding unconventional approaches maintains efficiency, but might miss opportunities that conventional thinking wouldn't discover. The Pykrete itself, as material, proved more durable than the project that developed it. The composite continued being studied occasionally by researchers interested in frozen materials and by engineers working in polar environments where ice construction remained relevant. The studies confirmed that adding fibrous material to ice creates stronger composite, but also confirmed that frozen composites have limited practical applications because refrigeration requirements restrict usage to environments where freezing temperatures exist naturally or where refrigeration can be justified economically. The limited applications meant Pykrete remained interesting rather than important, remained example of clever material science rather than foundation for widespread technological development. The human stories of individuals who worked on Habakkuk were eventually collected through oral history projects that interviewed surviving researchers and engineers and support personnel who had participated in project. The interviews revealed dedication and frustration and occasional humor about working on project that seemed increasingly unlikely to succeed, but which continued operating through bureaucratic momentum long after technical prospects had dimmed. The personal accounts provided texture that official documentation couldn't capture, provided insight into how people experienced working on ambitious project that was simultaneously exciting and disappointing.